So welcome to this class about kinetics. This is our first class. In this class, we need to understand the importance of energy in gas and liquid collisions. This is called Maxwell-Boltzmann distribution and activation energy. We'll use this concept in order to give a comprehensive account of the effect of the temperature and concentration on the rate of reaction, and also we'll be able to investigate how the rate of reaction changes with changing conditions. Okay, so if we start off here, asking how do we know if there is a chemical reaction? Now, there are some indications. These will indicate the presence or the absence of a chemical reaction. The color change is one of the indications that indicates the presence of chemical reaction, that chemical reaction took place. When gas is being given off, this also shows a chemical reaction has taken place. And when there is a change in temperature, that also shows that a chemical reaction is taking place. Okay, now what are these two reactions? These two reactions, the one here with the car, as you can see, is basically the car got rusted, it's rusting. And this one is explosion, as you can see. This is a slow reaction, can take years and years for this condition to happen. And the explosive reaction can take a part of a second. And this basically leads us to understanding of what the word rate means. So the word rate in English, it means anything divided by time. So if we were to divide the distance by the time, this will be speed. But here, because in chemistry, we're not using distance, so instead of distance, we will be using the concentration by time. So if we are measuring concentration, how the concentration is changing as the time progresses, that means we are basically studying the speed of reaction. And if we want to replace the word speed, we can say the rate of reaction. Okay, so if we have a reaction of A and B resulting in C, so basically if we manage somehow to look at the concentration of A and concentration of B at 1 minute after the chemical reaction, at 2 minutes, at 3 minutes, at 4 minutes, fine. So at 1 minute, maybe the concentration here of both of them was 1 molar. At 2 minutes, it was 0.5 molar. At 3 minutes, it was 0.25. So it's decreasing as the time increases. As the time increases, the concentration decreases. Why it's decreasing? Because it's being converted into products. Okay, so this is the rate of chemical reaction. Some chemical reactions are fast, and some chemical reactions are slow. Okay. Collision theory. Collision theory is basically a theory to do with explaining the different why different reactions occur at different rates. And the collision theory basically states two main things. It says that for a chemical reaction to happen, there are two things need to take place. First thing, that molecules must collide with each other in the correct and proper orientation. And the second thing, that there should be enough sufficient energy for this reaction to take place. So let's look at this. Let me just remove this writing here. Okay, so let's look at the first aspect. The first aspect here is telling us about the orientation. As you can see here, this diagram, we see that we have molecules, the red ones and the blue ones, they are colliding each other in the correct orientation, and therefore they are forming products. So this and this, they got in touch. They have head-to-head orientation, and therefore they form a new product of blue and red, blue and red. Now, this molecule and this molecule, they are basically orienting themselves in the beaker, for example, in the incorrect position, and therefore they will bounce back and they will not form a product. So that's what's meant by the correct orientation. Okay, now another thing here is that for the chemical reaction to proceed, the other aspect is the energy. So if we look at this here, we have this molecule, we have H2, Cl2 colliding with each other. Basically, they barely, touch each other, and then they'll bounce back. There is no energy to overcome the actual attraction between the ClCl and HH. In this case, in the other case, you have enough energy to cause the bonds to break between Cl, and then the amount of energy it will be used to make the other bonds to be formed, which is the HCl, and the new compound will be formed. Okay, so this is a successful collision. This is an unsuccessful collision, and similarly, that was a successful collision, and this is an unsuccessful collision. Okay. When we speak about the energy here, we need to learn new terminology. This term is called activation energy. Activation energy is defined as the minimum amount of energy required for the chemical reaction to proceed. So if the collisions with energy is in excess of the activation energy, the bonds will break and the new bonds will form. But if the energy that's resulted from the collision is not enough, then the reaction will not go ahead. So let's look at the activation energy in the energy diagram. So here you have the exothermic reaction. Here you have reactant. Here you have products. The products, they have less energy than the reactant. Now this hump here is called the activation energy. So basically, your reactants must have enough energy to overcome this hump in order to be converted into products. And same applies also in the case of in case of endothermic reaction. But notice here that the reactants, they have a lower energy than the products. All this is the activation energy, and this is the amount of energy absorbed from the environment. Now notice here, this is important to pay attention to, especially when we speak about the exam. For example, they may ask you to draw and label the diagram of exothermic or endothermic reaction. Okay, the next thing here is a Maxwell-Boltzmann distribution. So what is this distribution is all about? This distribution is basically looking at the number of particles against the energy, and this is done a long time ago in order to understand in theory how these particles are distributed along with the energy. So as you can see here, if we take a specific gas, let's say methane, for example, or hydrogen, so this area under the curve here is representing the number of particles of that gas. So if we take an integration of this area, this will give us the number of particles. As you can see, most of the particles, they have this amount of energy. So most of the particles, they have a small amount of energy, because you can see this peak here. I'm not sure if this will appear in the video or not, but let me denote this. Most of the particles, most of them here, they will have this amount of energy. And obviously this is not useful because the activation energy is here somewhere. So this is the activation energy. So most of the particles of your compound, they don't have energy that is required for the chemical reaction. So you only have this portion. Okay, you have only this portion of particles that have enough energy for the chemical reaction to proceed with the chemical reaction. All this area under the curve it's basically full of particles. These particles, they don't have enough energy to proceed. And therefore, you need to do something. You need to manipulate conditions so that you increase the number of particles that will have enough activation energy. So basically, you want to increase this area here. So again, this curve is representing the number of particles of your gas. As you can see, most of the particles, they have low energy. And if we say this is your activation energy here, so under the curve in this area, you have a very small number of particles. So what we need to do in the next few slides, we'll be looking at the different factors that can help us to increase the number of particles in this area. Okay. So what factors do you think can help us to do so? Think about it before you proceed with this video. Okay, so the first factor that we can speak about here, basically just a continuation of the similar thing here. As you can see, the shady area is the area where molecules have enough energy to proceed, and this area, the majority of the area here, it contains molecules with low energy. Now, if we speak about concentration, think about it. If you have two beakers here, this beaker has 10 molecules, and this beaker has 10 molecules. You mix them together, and you have 20 molecules colliding with each other. Now, this beaker, in another experiment, has 1,000, and this beaker has 1,000. You put them together, and the total is 2,000. So what's the big deal about this? The big deal here is that you're basically increasing the chances of having effective collisions. Don't you remember when we spoke about collision theory? Collision theory focuses on two things. First, the orientation. Second is the successful collision that will lead to enough energy between the two molecules that will lead to the formation of new bonds. So now you have 1,000 molecules here, you have 1,000 molecules here. So the chances of having collisions with enough energy to overcome the old bonds and form new bonds is basically much bigger than having a small number of molecules. And when we speak about number of molecules, obviously we're speaking about concentration. So as you can see here, in this case, where I'm shading now, we have a low concentration. We have low concentration here. Now we increase the concentration. That means we increase the number of molecules. And as we increase the number of molecules, we also increase the particles that have enough sufficient energy to proceed with this chemical reaction. And this line here that I am shading with red is showing that. So this new line contains the old line and the new one, which is all this. So all this area here is basically representing the number of particles that will have enough energy to proceed in the chemical reaction. So this is the first factor. First factor that you can manipulate is the concentration. And notice here as well that we didn't change the activation energy position. So the activation energy is the same. We didn't change the activation energy, but we only increase the number of molecules that have enough activation energy. Okay. So the next factor, think about it before we move on. Okay, so the next factor here is the temperature. So we have two temperatures here for the same reaction. Temperature one, as you can see, let me denote this. Most of the molecules, so here's the number of molecules. Here, basically, the number of molecules and their energy. So most of the molecules in reaction one, let's call it reaction one, they have low energy. When we increase the temperature, the shape of this graph change into this one, where I'm writing T2 or second reaction, if you like. Fine. So the shape of this curve, it leveled out, and therefore, basically, you increased the number of molecules that are having enough activation energy. So in the first case, the number of molecules that had enough activation energy was only this area. But when you increased the temperature and the curve leveled out a little bit, you have made the area under the curve for molecules having enough energy is to be all this, where I'm shading in orange now. So now by doing this change, by increasing the temperature, you are increasing the chances of effective collisions by increasing the number of molecules having sufficient energy for to proceed in the chemical reaction. Okay. Now, what next? What next here? We have also another factor that we can consider, which is the addition of a catalyst. Addition of a catalyst is a little bit different to the previous two factors. The previous two factors, the actual value of the activation energy remain the way it is. But in case of addition of catalyst will basically cause the actual path of the energy profile to change altogether. So let's see. So now this one here in red, as you can see, it has a high activation energy. So if we want to look at the activation energy here, it's from here down all the way here. And as you can see, you have to go all the way up and then form the products. When we added the catalyst, we formed this chemical reaction that follows the path of the blue line. So the activation energy in this case, I can color it with this, with a different color. So it will be from this point to this point in red. So as you can see, we have gone from all this to this small part of A. So the difference here is due to the addition of catalyst. So the catalyst basically provides an alternative path for the chemical reaction with a lower energy, Okay, as you can see in the diagram in front of you. So the actual value of the activation energy when you add a catalyst does change, unlike the temperature and the concentration. The actual value doesn't actually change. Okay, so the catalyst, if we want to speak more about it, we can say that there are two types of catalysts. There's something called homogeneous catalyst, and there's something called heterogeneous catalyst. Homogeneous catalyst is when the catalyst and the solution, the reactants, are all in the same phase. So if you have A and B in solution, and you add the catalyst in a form of solution as well, this is, you call it homogeneous catalyst. Now, if you have a heterogeneous catalyst, it's slightly different, because you may have A and B, the reactants, in the form of solution, but the catalyst in the form of solid substance or something supported on solid. And this is called heterogeneous catalyst. An example of this is the iron in the Haber process and the nickel in the hydrogenation of margarine and butter. Biological catalysts I'm sure that you have learned a little bit about this in biology. And this is basically, it works in a very much similar way. Uh, it works in a pure chemical reaction. So as you can see, this orange line here is for uncatalyzed reaction, and this blue line is for catalyzed reaction. This is the enzyme and the substrate. They're forming the lock and key, and then after that, the enzyme, it will separate from the products. Now, notice here that the enzymes, they work at a specific temperature, and in order for this enzyme to work effectively, it has to be at this temperature and pH. Okay. Next here, you will be provided with the activity and with the material that's sent to you. Next here, just a quick look about the rate of reaction. What does it mean? In the beginning of the class, I've said that rate means a quantity divided by time. And when we speak about chemical reaction, we're speaking about the amount of reactant or amount of product formed divided by the time. Amount here means concentration. So if we have a chemical reaction, let me write it. If we have chemical reaction, the like of A plus B resulting in C and D. So in the beginning of chemical reaction, the concentration of A and B will be high. And then as the time progresses, the concentration will decline and it will form C and D. So if we want to look at the rate of reaction from the perspective of reactant, so here the reactant's concentration is high. As the time goes past, then the concentration decreases. Now, if you want to look at the concentration or the rate of reaction from perspective of the product, so the concentration of the product at the beginning, when time was 0, it was very low. And then as the time progressed, as the time increased, the concentration of products also increased. Okay, so this is the definition of rate of reaction and how to look at the rate from perspective of reactants or the perspective of products. Now, interestingly, if you want to study the rate of a chemical reaction, you must have an instrument that allows you to monitor the concentration. And here the concentration can be the concentration of reactants, how the concentration of reactants decrease, or how the concentration of products increase. Okay. So if we were to join these together, these two graphs, you will be getting the concentration and the time. So the concentration in relation to the products will increase, and the concentration in relation to the reactants will decrease. Fine. Okay, next we'll be looking at the factors affecting the rate of the chemical reaction. Temperature, how the temperature will affect the rate of chemical reaction. Now, mostly the temperature will increase the rate of chemical reaction. So as the temperature increases, the collisions between the molecules increases, there is more energy, more molecules are able to overcome the attraction forces, forming new products, and therefore the kinetic energy increases, and the rate of the chemical reaction increases as well. Fine. So here is just to start with the temperature. Okay, so we don't have slides for the temperature. Anyway, the second thing here is the concentration. So as the concentration increases, what will happen? Again, the more successful collisions will take place, and the rate of the chemical reaction also will increase because there are more chances for successful collisions to happen. The next thing here is the surface area. Okay, now how to look at the surface area? If you have one big lump of reactant, and then you have the other reactant in green beside it, and then this big lump here, you divide it into small pieces. Which of these reactions do you think will take place faster? This reaction is basically a slow reaction, and the reason it's a slow reaction is because the interaction between these molecules and the big lump is only happening on the surface, but there are so many particles inside, they're not getting in touch with the other reactant. Whereas if you finally divided this compound here, this compound, if you finally divide it as you see in the image on the right-hand side, you will see that there is more interaction with the small pieces, and therefore the reaction gets faster and faster. Now, there is a practical example of this. So, for example, if you have a spice at home, let's say cinnamon, for example. So if you have cinnamon stick and if you have powdered cinnamon, which one will give more taste to your food or to your drink? Obviously, if you were to add spice in form of cinnamon to your food, if it is stick, it will affect the taste, of course, but it will not immensely affect the taste as much as if you have used cinnamon powder. So there is the reason here is cinnamon stick, it reacts with the water if you are cooking, for example, but it's only reacting on the surface, on that small surface. There is a small surface to be reacted with. Whereas when you when you crush down the cinnamon, when you ground it into small powder, you are increasing the surface area. You are increasing the chance of collisions, and therefore you'll be able to extract more flavor from that. Okay, the catalyst, as we have mentioned earlier, it will increase the rate of a chemical reaction. But the thing here is that the catalyst increases the rate of a chemical reaction in both directions. So if you have a chemical reaction like this, so the rate of chemical reaction, the front one and the reverse one, will be increased at similar rate. Okay, so it will not affect how fast the chemical reaction goes in one direction over the other. It basically just speeds up the chemical reaction altogether. Fine. The next thing here we want to discuss is how to measure the rate of chemical reaction. Now, I have mentioned this earlier. I said, to start with, what is the rate of chemical reaction? Rate of chemical reaction is the study of the concentration of the reactants or study of the concentration of the products. You want to see how this concentration decrease when you speak in relation to the reactant, or how this rate is increasing, the concentration, how it is increasing in relation to the product as a function of time. Fine. So any technique that allows you to do this measurement, then it is a valid technique. So what you need to do, for example, if you have this chemical reaction, you can sample. What does mean sample? Meaning that after 1 minute, you can take a sample of the solution containing these compounds. After 2 minutes, you take another sample. After 3 minutes, you take another sample and do the measurement, and then you can find the concentration for these components. Fine. Then also you can do continuous assessment for the in real time. So you can basically look at how the concentration is being changed in real time with the time. So as the time progresses, how the concentration is increasing. And to do this, any technique can do. So calorimetry can do, conductivity can do. If you know other techniques, the like of, for example, and that's what you'll study later on, the like of mass spectroscopy linked to HPLC, NMR. All these techniques can help in determining the rate of chemical reaction. But just to keep it easy, here there are some ways to determine, or some examples. So let's look at this. Now, if you react calcium oxide with HCl, and this is wrong, has to be corrected, and this will give you calcium chloride, H2O, and CO2. Now, what's happening here? In this case, when you react calcium, when you react the calcium carbonate with the HCl, it will produce the CO2. So in this chemical reaction at the bottom here, let me just mark it in case if you don't see it. And this one here, you have calcium carbonate, you have HCl, you put them inside the beaker, and then you close them with cotton wool. Why you close them with cotton wool? Because the CO2 will evolve, fine? It will be given off. Now, if you don't close this with cotton wool, the diffusion here, it will happen suddenly, and your measurement will be incorrect. So what you can do in this case, you can put these together, and in the beginning of a chemical experiment, the experiment might be, let's say, this number here, 12.06 grams. As the time progresses, after 1 minute, 2 minutes, 3 minutes, 5 minutes, 6 minutes, as the time progresses, what will happen to the weight here? It will decrease. So here you started with 12.06. Here it will be 11 maybe. Here's 10. Here's 9. Here's 8. And why is that? Because every time you are losing the CO2. So that's why the reaction will decrease. Now, the same reaction, you can study it in a different way. You can basically, you have the calcium carbonate, you have the HCl as a solution, and here you are measuring the volume of the CO2. You are measuring the volume of the CO2. So you're looking at the product, in this case, one of the products. In any case, here, when you measure the volume, you are increasing. So as the time passes, the volume of collected CO2 gas is increasing. So this belongs to this one. Now, for this one, as the time increasing, the amount of the weight here, or the concentration, is decreasing because you are losing more of the CO2, or it is being changed into a different entity. Fine. Also, you can compare between two things. Like, for example, if you were to use smaller pieces of calcium carbonate and large pieces of calcium carbonate, which one will give a quicker reaction? Now, this is when we have used large pieces of calcium carbonate. As you can see, the reaction rate is slow. And when we use smaller pieces of calcium carbonate, the reaction went much faster. How do we know this? Basically, if you draw a tangent, and I'll come to this in the next slide, but let's see. Okay, so as I said, this one also can tell us which reaction is faster if we were to use smaller or bigger pieces of calcium carbonate. And again, why do we do such an experiment? Or what's the reason behind that? The reason behind that is the surface area. In case of the smaller pieces of calcium carbonate, there is a larger surface area, and the opposite in case of large pieces. Okay. On graphs, how can we determine that? How can we determine the rate of chemical reaction? Okay. Basically, if you are asked to find out, let me just wipe these arrows. If you are asked to find out the instantaneous rate, and this is basically, it means the rate at time equals to 0. So you have to draw a tangent you have to draw a tangent here for the initial rate. And then you need to find the gradient. And the gradient here is the delta y over delta x. So this is the delta y, the initial and the x2 and x1. And this is the delta x. So this is the x-axis and this is the y-axis. Now, if you are asked to find out the rate at time 60, fine. So the instantaneous rate at time 0, this is the initial rate, and I showed you how to find it. Now, if you want to find out the rate or the instantaneous means at the moment of. So when we say instantaneous rate at a time of 0 means at the moment of 0, or you can call it the initial rate. Fine. Now, in case if you want to find out the instantaneous rate or the rate at the moment of time equals to 60. So here, this is 60, as you can see. Draw the tangent and do the same thing. The delta y divided by delta x. Why delta y divided by delta x? Because, as we said, rate equals to what? Equals to the concentration divided by time. So this side here, delta y, is representing the concentration, and delta x is representing the time. So at initial rate is at time, instantaneous time of 0, and any time else is called instantaneous rate at, you have to specify at what time. Now, if you want to find out the rate of reaction, the overall rate of reaction, then you can draw a line as you have seen here that encompasses all these points, and then you can take again delta y divided by delta x. I hope that video was useful to you. By the end of the video, you should be able to understand why we use Maxwell-Boltzmann distribution and the activation energy, and factors affect the rate of chemical energy, what's the rate of the chemical energy, how the energy can be investigated, and how it can be calculated. Thank you very much.